Hi everyone, welcome to our next Master Lecture in the Go Fly Master Lecture series. It's my pleasure to introduce founder and CEO, Gwen Leiter.
Thank you, Nidhi, and welcome everyone to today's Master Lecture. As you all know, GoFly's grand sponsor is Boeing. And in addition to Boeing, we are joined by corporate sponsor Pratt & Whitney, as well as our in-kind sponsors of Global Aerospace, Onshape, Total Sim, BRS Aerospace, Cases by Source, Fiberglass, Rockwest, Fergelli, and Voltaplex. In addition to them, we are joined by over 20 different aerospace organizations and STEM organizational partners around the world to bring you the Go Fly Prize and our programming. And today we are so very pleased to welcome Dr. Rafi Yoeli. Dr. Yoeli is the founder and the CEO of Urban Aeronautics Ltd. He founded and established the company in year 2000 in order to develop the world's first high-performance, compact, internal-rotor VTOL aircraft. The result is a scalable family of manned and unmanned aircraft known as Fancraft. The flagship unmanned Cormorant is currently in flight testing. Prior to establishing Urban Aeronautics, Dr. Yoeli spent the early years of his careers with the Israel Aerospace Industry, IAI, and with Boeing in Seattle. At IAI, he was part of the design team responsible for a number of programs, including the Laviv fighter aircraft and the West Wind 1125 Astra business jet, as well as the world's first UAV, the Scout. Dr. Yoeli is a licensed pilot for both fixed-wing and rotary wing aircraft and holds a Bachelor of Science in Aeronautical Engineering from Tel Aviv University. He also holds a Master's in Science in Aeronautical Engineering and a PhD in Artificial Intelligence, both from the Technion Institute of Technology. And so without further ado, I am so pleased today to welcome Dr. Rafi Yoeli to give today's Master Lecture.
Hello, everyone. Good day, and special thanks to the GoFly team for having me on board. I will start my lecture with a story dating back to 1992, and two MD-500 squadrons in the Israeli Air Force are being decommissioned. And we were sitting with the officers there talking about helicopters and what to do with these aircraft. And suddenly a suggestion came up. Why don't we turn them all into unmanned helicopters? And I, maybe foolishly, said, you know, how about we do that for you guys? And to my astonishment, everyone said, okay, go ahead. And there we were with requirement, a contract, and a helicopter to convert to unmanned helicopter. Now, I can tell you now, we've never done such a thing before. This was in my previous company. We did a lot of interesting work, but we've never converted a large helicopter to an unmanned helicopter. So we were with our backs to the wall, which is not bad in itself, and we started to think what to do. And it somehow occurred to me that the first step is to learn to fly a helicopter. You can't teach an autopilot of a helicopter to fly if nobody knows how to fly a helicopter ourselves. So I volunteered for the job, so to say, and I went to Florida and got my helicopter pilot's license. Then I went to Carlsbad, California, and did a conversion to an ND-500. And I came back. This all took a few weeks, but I came back quite proficient, quite, you know, knowing what to do about this MD-500 autopilot. This was the start of my interest in VTOL. And I learned three things from this experience with the ND-500. First of all, I became a better engineer. I understood what the VTOL is about. Second, we got some good ideas about how to design autopilots for helicopters, and I hope I'll have time to get back to that a little later. But the third thing was the most dramatic one. I hadn't realized until then what a big obstruction the large rotor and the tail rotor are in the performance and the utility of a helicopter. I mean, it's a fantastic tool, but this overhead rotor and the tail rotor is something the pilot thinks about all the time, and it's a huge limiting factor to the utility of the helicopter. So from that point onwards, I started reading more and more NACA reports and technical reports that were once classified, but they were declassified already at that time, about all the VTOLs, the VZ aircraft, the VZ1, the VZ8 by Piasecki, and many others. Chrysler had a VZ6, I think, and they were all with internal rotors. And I was basically determined to get rid of the rotor and see what we can do. But these vehicles didn't work very well. And the reports showed that they have had a lot of shortcomings. So I looked at what technology has done in the last 40 years. Now it's 50 years, it's 40 years then. To maybe improve those airjeeps. Now, engines have developed considerably. Composite materials weren't available then, they are available today, lighter structures. Flight control, guys, flight control, sensors, something to help the pilot this aircraft in gusty conditions. But all of that was of major importance, but still the stumbling block was aerodynamics, the interaction of the rotor and the fuselage and the lift augmentation on the fuselage needed some work. So on our main journey, we went to the wind tunnel, but before we did that, 5 years later, in 1997, I was already flying the little DZ-1 Hummingbird replica of the Hiller flying platform that you can see on the page there. And it was a very, very interesting experience. And we learned a lot of that. And this was our entry into ducted fan aircraft design. But I was much more interested in developing a modern day sleek version of the Piasecki Airjeep. So you can see already that this is not going to be an ordinary lecture or a cookbook about how to design VTOL aircraft. So it's more of a personal journey, but there are some things on the way that I've learned from this journey that I'd like to share with you. So this is the kind of vehicle that we dreamed about, similar in configuration to the VZ8. And fast forward to 2018, 2019 today, I think we've come a long way. And we have something that resembles this and has 250 flights on it, and I'll tell you about it a little later. Now, step number one, if you want to go to this vehicle, is always physics. You start with the physics, and we started with the physics. And the physics for these vehicles is the same as it is for the Harrier jets and the F-35s. And as a matter of fact, also for birds and insects. And it's Newton's second and third laws of motion. And they, in aerodynamics, they're called momentum theory. And what they say basically, as you see to the right of the screen, is that if you want to create a lift force from a rotor, then you have basically a spectrum of choices. You can take a large mass of air, like in a helicopter, and accelerate it only a little bit. And for the same amount of lift, you can take a small mass and accelerate it more. And you get the same amount of lift. So as far as lift and weight is concerned, you can really get the same effect from a smaller propeller. Where you pay is in the induced velocity and the power, which is proportional to the force itself, the lift itself, multiplied by the induced velocity. So some algebraic manipulation of the numbers end up with two very common terms, which is disk loading, which is the weight of your aircraft divided by the area of your rotors, and the power loading, which is how many pounds can you lift per horsepower. And these are commonly drawn in the literature, in the aeronautical literature, on a log-log scale. And this is nothing more than the power equation. So that's the lift times the induced velocity. And you can derive it in a few lines, very simple. And you can see a straight line. So the higher the disk loading, the lower the power loading, as you can see. Now, it's interesting to see how do actual VTOLs fare compared to the theoretical line. And you can see many of them drawn here. This is a statistical chart. And of course, you can take every aircraft's weight and the disk area. By the way, you have to take the net disk area. So one propeller above the other don't count. So you need to count them like in top view to see their projected area. You know the power of the engine and so forth. The area for a Harrier would be the 4 nozzles that it uses, and the area for the hummingbird bird that you see on the left would be the swept area when its wings move, which is the same as for any other vehicle. So we see very, very small disk loading, very low disk loading for the hummingbird. Then next to it are the eVTOLs and the quadcopters and so on. You see a bunch of helicopters, many, many helicopters, around the 10 pounds per square foot. Then you move to the right, and there are the V-22 and all the air jeeps. Notice that the power loading has gone down from 10 to 5 pounds per horsepower. So you really pay in terms of what you can carry. And you go further down, and down below, you see the F-35 in the most right-hand side corner. And this aircraft is really highly loaded. I'm talking about the fan behind the pilot's fuselage. Now, it's the same chart that I showed before, but you may see in yellow highlight those aircraft that have internal rotors. So those are ducted fans. And you can roughly see that they're a little higher than those aircraft that have a free propeller. And indeed, if you have a ducted fan, you have augmentation on the duct. And yes, there is a net benefit to that. But this is a bit misleading because momentum theory for a ducted fan is a little bit different because the air does not contract behind the ducted fan. Anyway, there is a theoretical line for ideal ducted fans, which just shows you how difficult it is to get to a high efficiency with a ducted fan. So ducted fans are indeed challenging, but still the overall benefit over the free rotor is there for everyone to see. Now, I've marked for reference the famous Bell 206 helicopter. The ND500 is next to it, and so are all the others. They're very low. They're between 5 and 10 pounds per square feet. And the reason I marked out the Bell 206 is just for reference because remember this yellow thing we wanted to build? We do want it to have 5 or 6 seats, just like the Bell 206. And we actually wanted to have the same performance, same speed, same range, but without the overhead rotors. So this Bell 206 will be our reference helicopter. Now, will we succeed? Where to pick our design point on the chart? There's no way to tell. Any point here is really as good as the other point. So I wanted to change this chart a bit. Of course, I can't change the data because it's statistic, but I can change the axis. How about if instead of disk loading, we would show the data, we would redraw it in a minute, and we'll show it shown as the inverse of disk area. So instead of pounds per square feet, we'd show the disk area divided by the weight. And on the vertical axis, we would not show power loading, but we would show power over weight and not weight over power. Before I even show you the data and how it's drawn, I already can see a big advantage to these axes. And the advantage is that we have a common denominator, and the common denominator is a pound of weight. So look, if you will tell me what is the disk area that you're allocating to your aircraft per pound of weight, I can probably tell you immediately by looking at this chart how much power you will need for that same weight, just by looking at the chart. So we'll see it in a minute, but before we do, I want to make another small change. I don't like the log-log scale. So if you'll allow me, I will just use a linear scale, and let's see what we get. So here's the same data exactly, drawn against the inverse of disk loading, inverse of power loading on a linear scale. Now this, when I first saw this, some of you may have seen this before or may have played with this before, but I saw it for the first time when I did that. And this was a huge surprise for me. Because now the chart is really talking to me and telling me things that I didn't see before. And suddenly momentum theory is a synthesis tool. So let me show you why it's a synthesis tool. Here's your Bell 206. And look at all the other helicopters. The other helicopters are very, very similar in their power per pound. And they vary very much in their disk area. So there's a large variety of disk area per pound, but not a big change in the power for the helicopters. So this is something to think about. But we don't want another helicopter, do we? What do we want? We don't want a car-sized air taxi. Where would the region for a car-sized air taxi be? We'd like to have very compact dimensions, internal rotors, but we wouldn't want to risk too much power. So isn't this the corner where you would probably aim for if you were to design a modern air jeep or a flying car? But there are other constraints. For example, if we ever want to move with this vehicle on the road, we're limited to 2.5 meters. This is almost an international limit that's almost identical in all the countries. So the highway patrol lets us move on the highway, even on a truck, for example, being towed on the highway, but we cannot be larger than 2.5 meters. So I passed a dashed line there. We do not want to be right of that line. Another thing that I want to mention in terms of power, there are many engines to choose from, but the truth is that the Bell 206 engine is a 420 horsepower Rolls-Royce engine. There are 3 or 4 manufacturers that manufacture helicopter engines that go higher than that, but most of them end at around 1,000 horsepower, and then there is a gap, and the next available engine is around 1,600 horsepower. So I've drawn a line, which I took on ourselves to limit our power to 1,000 horsepower. That would be an Ariel 2 by Turbomeca, would be an HTS 900 by Honeywell, would be a Pratt & Whitney 210, or a Rolls-Royce C47, for example, just to name, I think, most of the engines that are in this category. So there you have 2 lines, and they're still within that region. And there's one more bonus that we can get, which is that if we choose the point where the tangent to the line is at the approximate angle of 45 degrees, then for every 10% increase in weight of the aircraft, we would only need approximately 10% of power change. So this is a kind of linear region of the graph. And yes, this is our choice. And you see now a green dot of our Cormorant, which you see in the picture to the right. You can see it in our hangar. It's a 1-ton vehicle powered by an Ariel 2. You can see it flying, one of 250 flights that we've made with it. It weighs 1 ton. It flies very well. And this is our design point. Nothing other than that. Thank you, Momentum Theory. Didn't cost us a penny. No wind tunnel tests, no months of analysis. It was all achieved for free, just by looking carefully at momentum theory, being critical of information that we absorb, and with a deep, deep sense and desire to understand the underlying principles, not to settle for the first graph that you see, but explore it and play with it and see what you can get. And look at what we've achieved with actually no extra analysis or work, just by looking at the graph. Just to illustrate my point, would anyone have guessed that this is the optimal location in terms of disk loading and power loading for a future flying car? City Hawk, by the way, is a similar chassis, similar size to Cormorant. It's a little heavier because it's twin engine, but again, basically in the same area of the graph, and has a high power, but an available, not too expensive engines, and it has the same performance as the Bell 206 helicopter. So in that sense, I think we've achieved our goal that we set at the beginning of the journey, all just by using momentum theory, but using it wisely. I'd like to say a few words now about an issue that is very different from what I spoke until now, that bothers me a bit, and I want to share it with you. And that is our sometimes not so objective relationship with the past and past projects. Look at this chart for a minute, and I'm sure almost everyone who's watching this now knows this wheel of misfortune, as it's called. Excellent infographic done by Michael Hirschberg, I think, which shows all the experiments that were done in the 60s and 70s, divided into categories. Beautiful chart. You can spend hours with this chart and see what was done and so on. Only a few emerged. all of these aircraft were stopped, except the V-22, the tilt rotor, started with the V-15. Now the V-22 is in service. There were tilt rotors then. The F-35 also came out. I mean, there was already some fan in fuselage tested back then. The Harrier, of course. And maybe the VZ-8 has been resurrected due to our almost 20 years of work. We don't know yet. Now, because so many concepts didn't make it to production, this chart is universally known as the Wheel of Misfortune. But that's where many people get confused. And I've heard many people say that because these projects were canceled, we need to look for new ideas. Is this true? Well, maybe not. But I can tell you that there were very smart people behind these programs. And I must tell you that most of these aircraft were outstanding aircraft. They were very successful aircraft built by hugely talented people. And why aren't they in service? You know, there's so many reasons. A general moved on to another position, and the general who took his place didn't want to continue. A conflict like the Vietnam War, for which something was conceived, may have ended. Money may have ended. The inventor may have died prematurely. Or, you know, sometimes these programs are just budgeted as an experimental program. And they're very successful, but there's no follow-up. So again, the fact that they're not in service today doesn't mean that they were bad aircraft. And I'm saying this because if you want to design a new VTOL aircraft, do yourself a favor and go and read and learn and look at the NACA reports and look at the flight reports and learn about each and every one of these aircraft, because these are, number one, fascinating stories. Number two, the people who designed them didn't have the technology that we had today. They had a much more difficult task, and I raise my hat for them. Speaking about hats, we see sometimes, you know, even 20s and 30s era movies, black and white, with people moving a little fast. They look like a slapstick movie, and they wear top hats. And in the background, there's a helicopter. But we think it's funny. We don't take them seriously. But these people are brilliant people. They paved the way for us. And don't be misled by how they looked, by the black and white movies, by the bad videos, and so on. Some of these were great aircraft. So with this point behind us, I want to move on to something else that maybe is connected to this, but a little different. Is anyone here involved in VTOL urban air mobility? If you are, you might want to look back and see that millions of passengers were flown in a decade of helicopter flight. New York Airways, Massachusetts Helicopter Airlines, Los Angeles Airways. What happened? Where are all these helicopters? Why was this service stopped? I will leave it to you to find out, but it would be worthwhile to do that. And what happened to this idea? Do you know that of these aircraft, all these aircraft flew very well. And you know, they were even FAA certified and they were commercially available. You could buy them. So where are they? Why aren't they around anymore? Read about it. I leave it to you to find out. The question is, will we succeed this time around? We might, but not if we fail to learn the lessons from the past. And it's very important to go and see and find ways to overcome them and learn from other people's experience. I want to move to almost today's time for us and to say a few words about full-scale prototypes and demo aircraft. So I think everyone knows and realizes that a few things can elevate you more than a full-scale prototype of your creation, of your idea that shows what you want to do, what you're proposing in full scale. And I want to share with you a few bits of wisdom from my own experience of a few decades of constructing and testing and building a number of prototypes and demo aircraft. Now, I want to just warn everyone that this is my way of doing things. I'm talking as companies, then their way of building prototypes and demo aircraft is probably different. So I'm talking about a small group, limited budget, limited time, and to everything that I say, by the way, in this talk, and also especially what I'm going to say now, you have to apply your own judgment. You have to decide, do you want to go in the same way, and do you want to make the same decisions, and do you want to have the same kind of risk management that I've employed over the years? So it's your choice. I just want to tell you a little about my journey and what I learned from it. So we're designing a demo aircraft, and we don't have a lot of money, and we want the shop to start working. And absolutely, definitely, we don't need drawings. We don't need CAD. We can stay with sketches. Actually, your colleagues will appreciate a nicely drawn sketch over a CAD drawing anytime. And I suggest improve your sketching ability. Invest some time in that. And there are courses for that. And another big advantage of sketching is that if you give your workshop a sketch, you leave some of the design to them as well. So they're not just executing a whole list of instructions on something that you've designed from A to Z, but they're taking part in the process. They come back to you and they do their own sketches a little bit, and it improves communication considerably. CAD consumes a lot of time. Computer-aided design, Unigraphics and SolidWorks and so on, they're great programs. If you really want to advance, if you're not in a big company, if you're competing for, let's say, the GoFly competition or any other competition, and you don't have a lot of money, go ahead and use CAD if you need an outer mold line of something, or if you need something very accurate. But otherwise, I prefer not to. Now, some of you will say, yes, but machining, we have a lot of parts that we're machining, and in order to go to send a file to the machine shop, you must have a CAD drawing. And that's true, But I will tell you another thing. If you look at World War II aircraft, and now we're going back some time in the past, most of the parts were done with sheet metal. There's almost nothing that you cannot do with sheet metal and certainly composites, and there's no need to use so many machined parts on a one-time concept demonstrator. Just my piece of advice. Here are some more things to remember. In all the programs that I've done so far, I've made a point of taking an engine or a motor, if it's an electric motor, with 25–30% more power than my most severe analysis. Now, taking a more powerful engine almost doesn't influence your design. It sometimes doesn't even add too much weight, and it's worth it, because if you end up with too much weight or too little performance and so on, this overpower can compensate for it, and you can still show your demo when the time comes. This also enables you to tolerate extra weight. It shouldn't be overdone, but for now, leave yourself some freedom not to save the last ounce of weight on the structures, landing gear, rotors, transmissions. Give them some margins, give yourself a margin, and you'll be able to do it in half the time and a little bit heavier. Now, two rather more severe recommendations, and you really need to be a little more experienced to take these two on yourselves. The first one is to eliminate subcomponent tests. What I mean, for example, if you're building a new VTOL aircraft that has an engine and power transmission, which is shafts and couplings and gearboxes and so on. So it's very common and makes a lot of sense to first of all run these gearboxes on a stand and run the rotors on a stand if these are new rotors. Run the whole thing on a stand, but run them individually first and make sure that they work together. We usually don't do that. We usually assemble them, put them together, and run them together for the first time. We found that this saves a lot of weight. If something goes wrong, if there is a little vibration or something doesn't fit, it'll tell you. It'll tell you, and then you can just fix that, and you're done with the rest. So a lot of time, a lot of money is really saved by putting the whole machine together and firing up the engine, and not flying it first, of course, tie it to the ground and see what happens. So this is another recommendation. This is our initial flight of the Cormorant. It had skids in the beginning. It now has wheels. So what did we do? We tied it to the ground. The rotors were there, the transmissions were there, the engine was there, the fly-by-wire was there, and we fired up the engine, and this is the first time this whole thing started turning around. So we did the first run, we tied it to the ground, and then we had to do an endurance test, right? You can't just go ahead and fly around the patch with a gearbox that has 7 minutes of ground testing. This is totally irresponsible. So the next step is usually getting back now to the stand, or running the gearboxes for 50 hours or 20 hours or as much as you like. But we were eager to get up. We wanted to get up in there, and the flight control engineers were very frustrated that the whole aircraft runs, everything turns, wind, there's everything, and the aircraft is tied to the ground. So they asked us, could you please get this aircraft just 2 feet up so that we can get some air on our control vanes and see how our flight control system works. So we did that, and the complete endurance run on this aircraft was done with the aircraft hovering low above the tarmac. Again, some risk, but a lot of time saved and a lot of lessons learned. So, you know, it's like when you walk in a field and there's full of stones that are unturned and you want to turn every stone to see what's underneath it. It sometimes happens that you reach the end of the field and you look back and some of these stones have turned themselves without you having done anything, because your whole aircraft is now working and talking to you and telling you what it's good at and what is not. I want to also mention again something about the flight control. Remember my story about the MD-500 helicopter? About us, first of all, going to fly and getting the intuitive feeling of how this autopilot should work. Well, believe it or not, all the demo aircraft that I've built since, we've done the same thing. And on this Cormorant aircraft, we've done something very, very unusual. We first of all built a 6 degrees of freedom simulator with a big dome and a good representation based on wind tunnel tests of this aircraft in 9 degrees of freedom, actually, also with the controls and everything. And we organized a workshop which lasted a few days and gathered 10 of the best test pilots we could find and asked them to fly the aircraft and find solutions for how to fly the aircraft, how to transition from hover to forward flight, how to climb, how to descend, how to do a quick stop. Not many engineers know what a quick stop is, but you need to have a quick stop on such an aircraft, and you don't have an articulating rotor, and it's challenging. And what about the classic question of, are we going to have a collective or a throttle? And how are we going to command the top level flight control laws and so forth? So these pilots sat and worked and came up after a few days with a solution that had it all. They were all very happy with the handling qualities of the aircraft in the simulator. We later, by the way, confirmed it via ADS 33, that indeed this was a very good flight control system. And you know what? We burned their know-how and their recommendations into the flight control computer. And believe it or not, this is the first time that we let an engineer touch the flight control computer. And then they went ahead with their time domain and frequency domain and did all the filters and everything like engineers know how to do. But all the know-how of the test pilots is still there. And you know what? When we take this unmanned aircraft and we put a pilot seat on it and we start inhabiting it with people, this pilot has already flown this aircraft. So all we need is really to attach controls to that aircraft, and it has basically already been flown by a human. So these are ways to save time, save money. My recommendation, get the pilots in the loop soon. They know how to fly aircraft better than engineers, and use them to reduce your risk. Now be vigilant, be careful, don't rush, but don't be afraid to leave some stones unturned. It doesn't come in a day. There's no recipe that can tell you how to get to the point where you can take risks, trust your intuition, and really break the mold. But, you know, choose the difficult path, choose the less traveled path, and never stop learning. This is what I've found. I'll tell you a story. When I was a young student, I had a professor, Professor Shatsky, who was recommending to us that when we graduate from aeronautical engineering school, we don't go to work as an engineer, but spend a year in the workshop, just like a workshop apprentice. We didn't take his advice, of course. I mean, we all wanted to start our careers. And looking back, you know, this was the right decision. I mean, nobody in their right mind would really not go and be an engineer after you got your diploma. But I can tell you that all of us in that class who then worked for a few years as an engineer, but then took a break for a year or two and did something else, came back much better engineers than those that had stayed for many years from the day they graduated onwards. So my recommendation to you is to invest in yourself and take a break. This is a very unusual recommendation where we're talking here about designing a VTOL aircraft, but I'm totally serious, and I'm talking about you know, in a perspective of a few years. You know, go fly as a bush pilot in Alaska for 5 years, or get a job in one of the overseas aerospace companies for a year or two. It'll broaden your mind, and you'll come back a much, much better engineer that you are already. Oshkosh, Wisconsin. Go there, spend time at the workshops. This is the Experimental Aircraft Association. Very, very worthwhile. You'll learn a lot, you'll be inspired, you'll see how aircraft are designed. It has given me a lot. Practice sketching. I already talked about that. I can tell you that I remember each time a senior engineer took out a thick pencil from his or her shirt pocket and sketched an idea on a blank piece of paper, everyone around this person was silent. Everyone was listening. Practice sketching, it'll pay off. This will pay off tremendously. Learn to fly. If you're an aeronautical engineer, if you're a fixed-wing engineer, go fly fixed-wing aircraft. If you're helicopter or VTOL designer, go and fly a helicopter. And don't just take a check ride. Go and get your private pilot license. Go and learn how these aircraft look from the inside and how they look from the perspective of the people who use them. Thank you very much. Gwen?
Thank you so much, Rafi. A lot of critical and important information in your lecture here. We have a couple of questions for you coming in. The first being, what would you have done differently at the very beginning of getting your company going from a non-technical perspective?
I don't know. I don't know. I don't think, looking back, I don't regret anything, and I don't think I would have done it differently. Now, I want also to, I can maybe understand where this question is coming from, because you see, it's very scary to raise money on the move, to do something and then to advance a little bit and then to raise a little more money and so on and so forth. It's a really unusual way to work. This is how I've worked in the past. It has been scary at times, but you can sit and raise money the whole round, and then start working. But I never had the patience to just sit and wait for the full funding. There was some funding. There was a good business plan. It's always a business plan. So I'm sorry. I don't regret anything. I think this is the right way to go. If you're a small company, especially if you're almost an individual or just working 2-3 guys together, this is the way to go, in my opinion.
Great. Can you elaborate a bit more on the engine models you think that would work well for GoFly flying devices?
I'm sorry, but I can't because these are electric engines, electric motors, I guess, and I must say, and this is something I should have mentioned in the lecture, all the work that I've done in the last 20 years has been a moderate disk loading aircraft that need high power, and they cannot be operated with batteries. We are looking into the future to power our aircraft with hydrogen, and we're making very good advancement using fuel cell stacks, and it looks very good. So this is, in my opinion, the way to go. But we don't have too much experience with electric motors. If this was the question, I hope I understood the question.
So how does one avoid the wheel of misfortune? Or in other words, how does one working on their GoFly device build something that will actually be used?
So I think the wheel of misfortune is an unfortunate term. I don't think it represents these aircraft. The GoFly competition is what it is. It is a competition. And if you think, if you concentrate, and if you read, and if you understand, and if you don't just put something together and go fly, but you really think about what you're doing, you may be ahead of the rest, and you may find a really good. I was very impressed with the parameters of the GoFly competition. I think they were very wisely constructed, and you have to compare oranges and apples and pineapples and bananas, and you have to learn to do that. It's very difficult to do, and it's very challenging. I think that the motors are part of the story. They're not the whole story, but I'm sure that the people who are competing in the GoFly competition know the area very well. They should. I hope they do.
Rafi, you had, in one of your very first slides, you had pulled up a chart of all of the aircraft in terms of where they sit. Is it possible for you to pull that up again? Or perhaps mention, sort of discuss where you think the GoFly and GoFly devices sort of fit in a sweet spot on that chart.
Yeah, I can show you that just a minute. Okay, so I'm sorry, I have to go like this. Yeah, okay. So we're talking about this chart, right?
Mm-hmm.
Yeah, so you can see at the disk loading of 2 pounds per square feet, you can see an icon of a quadcopter there. If this aircraft needs, and I don't remember all the details of the GoFly competition, but if this aircraft needs to hover only to take off vertically and land vertically, and then spend most of its time flying, then it could use a wing to support it, and then it wouldn't need such a low disk loading. So you could have a higher disk loading use very high power for the jump takeoff and then for the landing, as many vehicles out there are doing. But this, of course, increases the footprint of the aircraft. But generally, the electric-powered, the battery-powered aircraft are on the left-hand side of this curve, so left of the helicopters, because their batteries are heavy and they have a limited power compared to jet fuel and gasoline. And therefore, you have to carry a lot of dead weight, and you have very low power, so you must increase your disk area and reduce your disk loading if you want to hover for an extended period of time.
Okay, perfect. So for developing quickly and prototyping early, what is the best time for system safety analysis? Is it a worthwhile activity before the concept is even proven?
It's always a good thing to do. It depends how formal you get into the process. You must always take a piece of paper, a pencil and paper, and look at the fault tree and estimate. I mean, look for the weakest link and brainstorm with your, with your colleagues or with others or with an expert. Show them what you're doing and think about what can go wrong, and make sure there's no weak link in the aircraft. And if there is, then there's some redundancy. We're talking about aircraft that are flying. Some have people flying on them. This is not a joke. So even on the demo, in the demo phase, all that I've told you in this lecture, notwithstanding all that I've told you in this lecture, you have to get to such a safety level that if you want to fly people in experimental aircraft and you don't have this level of safety, then you absolutely need an emergency parachute or an ejection seat or something to save the crew, at least, if something goes wrong. So yes, the FAA has criteria for that. And everything that we've designed that ever carried people on board, we were extremely careful. We were sticking to the numbers of the large aircraft and so on. We did it usually with a lot of redundancy and backups and so forth. But there's no way around it. Don't take the risk. Don't take risks in that. I mean, you can take risks in other things, but not when people are on board.
Mm-hmm. Absolutely. There was also an adjusted chart that you had shown, I think maybe a couple slides down, if you could show that again.
This chart?
Yes. Mm-hmm. And a question we're getting is that if GoFly will be able to post these charts for the teams to be able to review later, will it be okay with you if we're able to take these individual slides and share them with the GoFly community?
Yes.
Great, thank you for that. So I think, and we're actually at time now, so that works perfectly. That is the extent of our questions right now. Rafi, so thank you again so much for your time, and I will invite Gwen for any closing thoughts.
Thank you.
Hello, and Rafi, thank you so very much for that illuminating talk. I know that our GoFly teams will learn a tremendous amount, and personally, I loved how you used the data to fine-tune exactly what is best for your way forward. I think that will be incredibly helpful to our teams. So I truly appreciate your time here. GoFly teams, we know that you are now very close to submitting your phase 2 submissions. We look forward to seeing those. They'll due February 6th. And for everyone else watching, this lecture. We wish you all of the best in your flying endeavors. And thank you once again to Dr. Rafi Yoeli for a wonderful master lecture. Thank you.
Thank you.